Hey everybody, welcome back to Fastware. So, today I want to talk to you about multi-threading. It is a topic that I had to argue and discuss actually more times than I can count, and inevitably ends up with me just face-palming myself. So, anyway, from what I can gather, there are three significant misunderstandings regarding multi-threading. So I'm gonna have to rant now, bear with me. Uh, First chapter entitled Run It in a Separate Thread, and it's faster, right? Well, that would be nice. Many times over, I have seen actually code that is not suitable to run in parallel. However, somebody thought it would be better to spawn a thread of one task or another. And as a result, you can see literally mutexes littering the code base, and hey, it sometimes freezes, or hey, it crashed. Inevitably just becomes part of doing business, and everybody tolerates it. Anyway, I have experienced this personally when working on a Chromium project, and what I have seen there still haunts my nightmares actually. So over 80 threads running simultaneously in the browser process alone, right? And if you don't know why this is horrifying, wow. So I guess you will learn then. Anyway, so threads are actually a hardware feature, right? So for example, a CPU core is a thread. Generally on modern hardware with hyper-threading, you can run two threads on a core. So basically each core representing two threads. However, so if the CPU has now 4 cores, that means you can only have 8 threads running in parallel, right? Math is elementary here. As another question arises, what happens when you have 80 threads, but your hardware supports only 8 of them? Now, if you think for yourself, hey, wait, it's too much, I don't care, well, you're part of a problem, and that needs to be addressed. Anyway, oversubscription is actually a common problem where software threads outnumber the hardware ones, and the CPU has to schedule each task, migrating it from a core to a core when one becomes available. So the thread migration actually involves cache invalidation, data migration as well, and so the more threads you have, the less time each task can run before being interrupted, to make space, to make time for another process to make progress. I hope you get the picture here. Anyway, chapter 2. It's simple, just put a mutex around it, right? How difficult could it be? It's trivial, right? Well, anyway, so a simple statement that access to a variable from multiple threads must be synchronized, of course, is correct. However, I think there is a lack of understanding about what is actually involved in making that happen. And I think this ignorance stems from either not knowing, not wanting to know, or just simply not caring about how this CPU cache hierarchy works. But I think it is critical to understand if you want to actually understand the primitive synchronization in multi-threaded applications. So invalidate on write mechanism actually ensures the data integrity in a cache, whereby a write to a primitive invalidates an associated cache line in the caches of other cores. So data then is reacquired from the main memory on a successive read from a different thread, right? So, but there is a crux in this problem. So, different threads attempt to read and write primitives residing on the same cache line, resulting in repeatedly invalidated caches, which just slows down data reads because you need to read from main memory, and that is slow. So we already looked at memory hierarchy latency in another video, so click the card to watch that video if you want to know more. So this behavior tends to actually make our applications slow, especially the poorly designed multi-threaded programs is just atrociously so. And I think many of us have experienced that. Chapter 3. Why is it so slow? I don't understand it. Anyway, continuing with the last point, this one is a bit more obscure, and probably you're right about now. You're asking, wait, what? I cannot handle this anymore. Why? But I'm afraid there is more, and it's actually not very pretty. So when you read or write a variable, a CPU does not just get that variable, but instead actually reads or writes the entire cache line associated with it. So most modern hardware have 64-byte cache lines, and here's the magic trick. In multi-threaded programs, writing to a variable invalidates the entire cache line. So hence when you consecutively read from another thread another variable within the same cache line, that causes the system to fetch data from the main memory unintentionally. This is actually called a false sharing, and it's considered a quite severe performance bug. But you can call it shit happens. You can avoid false sharing by aligning your primitives to 64-byte address boundary and padding a new space if necessary. And while actually C++ have a good enough language support to allow anybody to deal with this problem with relative ease, the standard library is actually quite notorious for making this problem more challenging than it has to be to solve. So it can be actually a real pain in the ass. Yeah. Anyway, we're here. So unfortunately, these problems associated with multi-threading are not trivial and require enough knowledge and practice to notice and to overcome. Crying in a corner about how difficult it is or it's too low level, I don't want to know, tends to not help, but ensures actually that these problems persist, grinding your projects to a snail crawl rather than rocket ship that probably you were aiming for, right? Well, I hope that with this theoretical background now, and maybe with a bit of practice, you'll be able to apply these skills and put them to good use. Happy threading! And subscribe for more content like this in the future. Leave a like, a comment, and I'll see you next time. Take care now. Bye-bye.